Okay, this is lesson 19 on convexity. Before I start the lesson, are there any questions about problems on mean value theorem, extrema, first derivative test, anything that we've been talking about for the two previous lectures?
I have a question from the homework
Go ahead.
number 33 in edition 5.
On what page? Or
It's
what section?
question section 4.3, page 226.
Okay. And which is the question? Which
Number
number?
33. It's number 33.
X plus 2 to the 2/3?
Yes.
Okay. So this is section 4.3, number 33. We look at the
Yes.
function f of x equals x plus 2 to the 2/3. And we want to find the critical numbers, if any, the open intervals in which the function is increasing and decreasing, and locate the relative extrema. So we have to first find the derivative. If f of x is x plus 2 to the 2/3, that implies that f prime of x is 2/3 x plus 2 to the 2/3 minus 1, which is 2/3. This is minus 1/3, so that's 1 over the cube root of x plus 2. And so where do we have a critical number? So f prime of x is not 0 for all x. F prime of x is undefined when the denominator is 0, which means x equals minus 2. So x equal minus 2 is the only critical number. So we differentiate x plus 2 to the 2/3. We get 2/3 x plus 2 to the minus 1/3, or 1 over x plus 2 to the 3rd, or cube root of x plus 2. And this is undefined when the denominator is 0, that is x equals -2. So at that one point, we have a critical number. Nowhere else is the function 0. Okay, any questions about that? Okay.
No.
So, sorry, is there a question?
No question.
Okay. So where is the function increasing and where is it decreasing? So f prime of x is increasing. Sorry, f of x, the function is f of x is increasing when f prime of x, which is 2/3, 1 over the cube root of x plus 2, is positive. So a fraction is positive. If the numerator is 1, the denominator has to be positive. So this is the same as saying the cube root of x plus 2 is greater than 0. And the cube root of a number is greater than 0 precisely when the number is positive. So from -2 to infinity, the derivative is positive and the function is increasing. F prime of x is the function f of x is decreasing when f prime of x, which is 2/3, 1 over the cube root of x plus 2, is negative, which happens when the cube root is negative. That means the number you're taking the cube root of is negative. That means x plus 2 is less than 0, or x is less than -2. Now, if you look at our original function, f of x equal x plus 2 to the 2/3, it's defined when x equals -2. F of -2 is -2 plus 2 is 0. And if you take x plus 2 and you square it, if this isn't 0, you get a positive number. The cube root is positive. This is greater than 0 for all x except -2. So this means that our function has to look something like this. At -2, the value of the function is 0. Oops, sorry, -2. At -2, let me make a better picture. At -2, the value of the function is 0. For x bigger than -2, the function is increasing. For x less than -2, the function is decreasing. So there is a relative or minimum at x equal -2. The function is decreasing and then increasing, and there is no relative maximum. So the relative extrema means a relative minimum or maximum. There's one relative minimum and no relative maximum. So that's the story. Any questions about this? This is a basic Calc 1 problem. Given a function, use the first derivative to find the intervals where the function is increasing and decreasing, and find the relative extrema, the relative maxima or relative minima. Any other problems you would like me to do? Happy to do more. Okay, then we go to section 4.4 on
Hey,
convexity.
Professor, I have another question, if you
Sure.
don't mind helping.
Go ahead.
Number 29 in edition 5. It's the same page.
Number 29, let me see. That's x to the 5th minus 5x over 5?
Yes.
Is that, yes? Okay.
Yes.
So this is, again, section 4.3, number 29. We have f of x is x to the 5th minus 5x over 5, which, if you like, you can write as 1/5 x to the 5th minus x. I mean, that's just a matter of choice, but. And then if you differentiate, when you differentiate x to the 5th, you get 5x to the 4th minus 1. The 5's cancel. So this is x to the 4th minus 1. So what are the critical numbers? The critical numbers are the points where f prime of x, which is x to the 4th minus 1, equals 0. And that only happens at two places, two real numbers, x equal +1 or -1. So those are the critical numbers. If you wanted, you could factor x to the 4th minus 1. That's x squared minus 1 times x squared plus 1, which is x minus 1, x plus 1 times x squared plus 1. And then you see directly that 1 and -1 are roots, and x squared plus 1 has no real root. So there are two critical numbers. There they are. Now, if you want to find where the function is increasing, so f of x is increasing for f prime of x equal x to the 4th minus 1 greater than 0, which is the same as x to the 4th greater than 1. And that happens in two ways. You can either have x bigger than 1 or x less than -1. If x is between -1 and +1, x to the 4th is less than 1. If x equals plus or minus 1, x to the 4th equals 1. It's x to the 4th is greater than 1 for x bigger than 1 and less than x minus 1. So if you have x equal 1, x equal -1, in this infinite interval, the function is increasing. And in this infinite integral, going to minus infinity, the function is also increasing. Okay. Is there a question about this? Anything? And similarly, f of x is decreasing when the derivative is negative, if and only if x to the 4th is less than 1, which is the same as saying x is between -1 and +1. So in this interval, the function is decreasing. So we know this function is going up, going down, and going up. And if we want to sketch this, so f of x has a relative maximum at x equal -1. Well, if the function is going up, what is the value of f at -1 or at +1? If you plug in x equal 1, you get 1 minus 5 over 5. That's minus 4/5. So this is -1, 0, and 1. And when x is 0, this is 0. So, oops, sorry. What I said wasn't correct. F of 1 is 1 minus 5 over 4, which is minus 4/5. F at -1, x to the 5th is -1 minus 5 times -1 over 4, over 5, excuse me. That's plus 4/5. So at -1, the value is 4/5. At 1, the value is minus 4/5. The function is increasing till it gets to -1, decreasing till it gets to 1, and then increasing again. That's what's going on. Increasing, relative maximum, decreasing, relative min, increasing again. In fact, if we wanted to look at a graph of y equals the derivative f prime of x, For x less than -1, the derivative is positive. It's 0 at -1, and then it's negative. It's decreasing until it gets to x equal 1. Sorry, let me say this right. The derivative is positive, that means above the x-axis, for x less than -1. For x between -1 and +1, the derivative is negative. It's 0 at 1, and then it's positive. It's increasing for x bigger than 1. So this is approximately the graph of the function of f of the derivative. And you notice, so around -1, it goes from positive to negative. So the derivative at -1, the function is decreasing there, it's negative. At 1, the function goes from negative to positive. So f prime of +1 is greater than 0. And we notice the following fact in this example. At -1, where you have a relative maximum, the derivative of the function is 0, but the derivative of the derivative, that's what we call the second derivative, is negative. So at this relative max, f prime of -1 equals 0, but the second derivative of -1 is negative. At x equal 1, the derivative goes from negative to positive. That means it's increasing. So the second derivative is positive. So at the relative maximum, f prime of 1 is 0, it's a critical number, but the second derivative at 1 is positive. And we'll see in a moment that this is an example of what's called the second derivative test. If you're looking for a relative maximum or a minimum, it's going to occur where the first derivative is 0. But how do you distinguish a relative minimum from a relative maximum? If the second derivative is negative, you have a relative maximum. If the second derivative is positive, you have a relative minimum. So we'll see that in a couple of minutes. Any questions about this problem? Okay. Then we will go on to section 4.4, which is concavity. And there's several ways to define concavity. And one, chosen by the author of the book, is the following. Suppose we have a function y equals f of x, which is differentiable. That means it has a derivative. On the open interval I. So we say, so this is the definition. The graph of f of x is concave upward if on I, so concave upward on the interval I, if the derivative f prime of x is an increasing function on I, and f of x is concave downward on I, if the derivative f prime of x is decreasing on I. So let me draw some pictures to give you sort of a geometrical sense of what it means for a function to be concave upward. Suppose the graph of y equals f of x looks like this. Now, wherever you take a tangent, so the tangent is the slope of the derivative. So there's a tangent. There's a tangent. There's a tangent. So to say the derivative is increasing means that these tangent lines are getting, the slope is increasing. So this is very negative, less negative, positive, more positive. This is an example of a curve which is concave upward. The derivative is increasing. So the slope of the tangent line is increasing. On the other hand, this is an example of something which is concave downward. These tangent lines are going from positive to less positive to negative. So this is concave up, this is concave down. Another way to see this geometrically is where the curve is concave up, it lies above the tangent line. So here's a tangent line, and around this point where the curve is tangent to the line, the curve's above the line. Here, this is concave down. Here's the tangent line, and around this point of tangency, the curve is below the tangent line. So that's a very good way to picture what concavity means. Let's look at let's look at one simple example. Suppose we have the cubic curve, the function f of x equals 1/3 x cubed minus x. So for this function, f prime of x is 1/3 times 3x squared minus 1, or x squared minus 1. What does the graph of the derivative look like? So if you look at y equal x squared minus 1, that's a parabola that looks like this. This is the graph of the derivative. This derivative is increasing for x bigger than 0. So for x bigger than 0, this curve, the graph of the function is concave up. The derivative is, sorry, the derivative is positive for x bigger than 1 and x less than minus 1. Right here is positive, here is positive. The derivative is negative for x between minus 1 and 1 in this region. So x bigger than 1, the curve is concave up. X less than minus 1, curve is concave down. And between minus 1 and plus 1, curve is concave up. And between minus 1 and plus 1, the curve is concave down. And in fact, if you were to graph y equals a third x cubed minus x, what does the graph look like? It's 0 at 0. It's also 0 at cube root of 3 and minus the cube root of 3. And here's minus 1 and 1. When x is equal to 1, you get a third minus 1. Minus 2/3. When x equals minus 1, you get minus a third plus 1. You get x equal to plus 2/3. So this function is increasing. Let's see, how do I? Sorry. Excuse me. So I said something wrong. When I'm looking at, so let me go through this again to make it clear. Here we have the function f of x equal a third x cubed minus x. If I differentiate it once, I get x squared minus 1. This is the graph of x squared minus 1. The derivative is positive for x bigger than 1 or less than minus 1. So for x bigger than 1, the function is increasing. For x less than minus 1, the function is increasing. And for between minus 1 and plus 1, the function is decreasing. So the function is going up until it gets to minus 1. Then it's going down until it gets to plus 1. And then it's going up again. This function is increasing for x. So f prime of x this is the graph of f prime of x, is increasing for x bigger than 0. So for x bigger than 0, I'll put it in red, this is concave up. I'll just say concave up instead of concave upwards. When x is less than 0, the first derivative is decreasing. So the curve is concave down. So in this region, the curve is concave down. So the curve is concave down. It gets to 0, it changes to concave up. So the concavity changes at x equals 0. And a point where the concavity changes is called an inflection point. So this curve has an inflection point at 0. Concave down, inflection point, concave up. And that is the typical and very beautiful behavior of a cubic curve, a polynomial of degree 3. Okay. So these observations are collected in a theorem, which is Theorem 4.7. Let f be a function, y equals f of x, let f be a function whose second derivative, not just the first derivative, but the second derivative exists on an open interval I, if the second derivative is positive for all x and I, then the graph of f is concave upward. On I. So concave up means the second derivative is positive. If the second derivative is negative for all x in I, then the graph of f is concave downward. On I. And that's just the definition, because a function is increasing if its derivative is positive. So concave upward means the first derivative is increasing. That means the derivative of the derivative is positive. That is, the second derivative is positive. And similarly for concave down. So let's look at examples. Example 1. We have the function f of x equal e to the minus x squared over 2. This is a bell-shaped curve in probability and statistics. That's what the graph looks like. We want to find open intervals where the curve is concave up and open intervals where the curve is concave down. So if we differentiate this, f prime of x is e to the minus x squared over 2 times the derivative of minus x squared over 2, which is minus x. Now, an exponential is always positive. So f prime of x is greater than 0 when minus x is greater than 0 or x is negative. F prime of x is less than 0 for x positive. So for x negative, the curve concave up. Oops, sorry. Where f prime of x is greater than 0, for x less than 0, the function is increasing because the derivative is positive. Increasing. F prime of x less than 0, there the function is decreasing. So this function is increasing until you get to 0, and then it's decreasing. What about concavity? Well, let's look at the sign of the second derivative. If f prime of x is minus x e to the minus x squared over 2, when we differentiate that by the product rule, the second derivative is the derivative of x, which is 1, so this is minus e to the minus x squared over 2, minus x times the derivative of e to the minus x squared over 2, which is minus x e to the minus x squared over 2. So what I have is, first of all, I can factor out an e to the minus x squared over 2, and this is x squared minus 1. So f double prime of x is equal to this. So f double prime of x is positive for x bigger than 1 or less than minus 1. And f double prime of x is negative for x strictly between minus 1 and plus 1. So this is minus 1 and plus 1 on the curve. The function is concave up till it gets to minus 1. It's concave up when x is bigger than plus 1. But between minus 1 and plus 1, the curve is concave down. So this standard exponential function, e to the minus x squared over 2, this tells us, the second derivative tells us where it's concave up, where it's concave down. Positive second derivative means concave up. Negative second derivative means concave down. Are there any questions about this? Well, this is a very important concept. Let's look at another example. So this is example 2. We have the function f of x equal x squared plus 1 over x squared minus 4. And we want to find the open intervals where this function is concave up and concave down. So we need the second derivative, which means we need the first derivative. The derivative is what? X squared minus 4 squared in the denominator. The derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. So this is 2x cubed minus 8x minus 2x cubed minus 2x over x squared minus 4 squared. So this is equal to minus 10x over x squared minus 4 squared. That's the first derivative. For the second derivative, it's minus, so let's differentiate this expression. You get x squared minus 4 squared squared, means this to the 4th power. The derivative of the numerator, which is 10, times the denominator, minus the numerator, times the derivative of the denominator, which is 2, x squared minus 4, times the derivative of x squared minus 4, which is 2x. So let's see, I can factor an x squared minus 4 out of the numerator. I get x squared minus 4 times what? I have 10 x squared minus 4. 2 times 2 is 4, times 10 is 40, minus 40 x squared. So what I have in here, and so of course, this cancels one of this, makes that a 3. And what I have here is 10x squared minus 40 minus 40x squared, which looks like minus 30x squared minus 40. So anyway, minus 30x squared plus 40. Oops, did I do that right? I think I'm off by something. No, looks okay. So these cancel. I can factor a 10 out of this. This is 10 times 3x squared plus 4 over x squared minus 4 cubed. Okay. So this is the expression we have to analyze. You notice that the numerator is positive always. 10 times 3x squared plus 4 is greater than 0. So the sign of the second derivative is determined by the denominator. So f double prime of x is positive if the denominator is positive, which means x squared minus 4 is positive, or x squared is bigger than 4. X squared bigger than 4 means x is bigger than 2 or x is less than negative 2. So for x bigger than 2 or fx less than negative 2, the second derivative is positive and the curve is concave up. Alternatively, f double prime is negative. If this is negative, x squared is less than 4. So x is between minus 2 and plus 2. And in this interval, the curve is concave down. So this is the second derivative. It's not defined when the denominator is 0. So this is only defined for x not equal to plus or minus 2, because the denominator can't be 0. For x less than negative 2 or greater than plus 2, second derivative is positive, curve is concave up. For x between negative 2 and plus 2, the second derivative is negative, and the curve is concave down. All right. So let me define an inflection point. So we have a function y equals f of x. The point C.
Professor, can you move the paper, please? Thank you.
The point C. So the function is, we have a function which is continuous and differentiable on an open interval. So continuous on an open interval I, and let C be a point in this interval. So the point C is called an inflection point. If well, let me just write it the way the text does. If the function f has a tangent line, that means a derivative at the point C comma f of C, and the concavity of the graph changes from up to down or from down to up at the point C. So an inflection point is a point where the concavity changes. So let's look at an example. And then there's just as a immediate a theorem that follows right away from the definition. This is point 4.8. If C comma f of C is at an inflection point, then either the second derivative at C equals 0, or the second derivative does not exist at the point C. And recall, a curve is concave up if the first derivative is increasing. It's concave down if the first derivative is decreasing. So at an inflection point, the concavity might change from up to down. So the derivative goes from increasing to decreasing, which means you have a relative maximum at that inflection point, and there the derivative is 0 or doesn't exist. So let's look at an example. So this is example 3. We consider the function f of x equal x to the 4th minus 4x cubed. So let's find where the graph y equal f of x is concave up, concave down, and has inflection points. So these questions about concavity are determined by the first and second derivatives. So here is f of x. If we differentiate it once, we get 4x cubed minus 12x squared. If we differentiate it again, we get 12x squared minus 24x. If we factor out a 12x, that's 12x times x minus 2. So f double prime of x, which is 12x times x minus 2, equals 0. At x equals 0, and x equal to 2. So there are two places where we could have an inflection point. This is not if and only if. This says that if there's an inflection point, then the second derivative is 0. So we have x equals 0 and x equal 2. This is where the second derivative is 0 at these two places. If x is bigger than 2, the second derivative is positive. That means the first derivative is increasing and the curve is concave up. If x is between 0 and 2, I have positive times negative. The second derivative is negative. The curve is concave down. If x is negative, this is negative times negative is positive. So here the derivative is positive, second derivative is positive, curve is concave up. So that is the story of what happens. And in the text, there is a nice sketch of the graph of this function. If f of x is x to the 4th minus 4x cubed, you can see that this is 0 at 0 and 0 at 4, and the curve is concave up and decreasing till you get to 0. Then it is concave down until you get to 2. And at 2, the concavity changes and it starts to go up again. So here, it's concave up, concave down, concave up. A cubic curve which means the graph of a polynomial of degree 3 almost always looks like this. If A is positive, this curve is going up, down, and up again. And typically there's exactly one point, C, which is an inflection point. And to the left of C, this curve is concave down, and to the right, it's concave up. A cubic curve almost always looks like this. There's some sort of degenerate cases like y equal x cubed that look a little different, but this is the general form of a cubic curve. Okay, so the last thing I'm going to do today is the second derivative test. So let f of x be a function where the first derivative at c is equal to 0, and the second derivative exists on some open interval containing c. So if the first derivative is 0, then you might have a relative minimum, or you might have a relative maximum, or you might not. But there's one case, there are two cases, when you can distinguish, when you can say exactly what you have. If the second derivative is positive at c, then c is a relative minimum. And if the second derivative is negative at c, then c is a relative maximum. And the third case is that the second derivative is equal 0, and then we can get nothing. We have no information. We could have a relative minimum, we could have a relative maximum, we could have neither one. So let me just prove part of this. Remember that the second derivative at c, this is the derivative of the first derivative. So this is the limit as x goes to c of f prime of x minus f prime of c over x minus c. But the first derivative is 0. We're told that f prime of c is 0. So this is the limit. So this expression, this term here is 0. This is just f prime of x over x minus c as x approaches c. Now, if the second derivative at c is positive, then this limit as x goes to c of f prime of x over x minus c is positive, which means f prime of x over x minus c is greater than 0 on some interval, small interval, containing this number c. If this expression is positive as x goes to c, from some point on, if x is close enough to c, this is positive. So there's some whole little interval where f prime of x over x minus c is positive. So if x minus c is positive, the denominator is positive, then the numerator is positive. And to say x minus c greater than 0, it's the same as x is greater than c. So for all x bigger than c, the derivative is positive. So that means the function is increasing for x bigger than c. If x minus c is negative, then this ratio is positive, so f prime of x is also negative for x less than c. So for x less than c, the derivative is negative, and the function is decreasing. So if it's decreasing, gets to c, and then is increasing, that means this is a relative max. So this is the important fact to remember is the statement of the theorem. If the first derivative is 0 and the second derivative is positive, you have a minimum. If the first derivative is 0 and the second derivative is negative, then you have the maximum. It's sort of counterintuitive in a sense. Where you have a negative, you have a max. Where you have a positive, you have a min. So we'll do one example, and then we're going to quit for the day. Suppose f of x is minus 3x to the fifth plus 5x cubed. And we want to find the relative extrema. That means the relative minima and maxima. So the first derivative is minus 15x to the fourth plus 15x squared. And when is the first derivative equal to 0? So let's see, let me factor out a 15x squared, 1 minus x squared. That's 15x squared, 1 minus x, 1 plus x. So f prime of x is 0 if and only if x is one of the numbers minus 1, 0, or 1. So these are the critical numbers. Those are the numbers where the derivative is 0. Let's take the second derivative. The second derivative is minus 60x cubed plus 30x. If I factor out a 30x, I get 1 minus 2x squared. Let's make a little table. X, f double prime of x. So our three critical numbers are minus 1, 0, and 1. So when x is minus 1, I get minus 30 times minus 1, I get plus 30, which is positive. Second derivative, positive. First derivative, 0, which means we have a relative max. When x equals 0, this is 0. So we have no information from that. We just don't know. When x equals 1, we get 30 times minus 1. That's minus 30, which is negative. So negative second derivative means we have a relative, sorry, second derivative positive, this is a relative minimum. Second derivative negative means we have a relative maximum. And the book shows us what the graph of this function looks like. Looks like that. This is the point minus 1. This is the point 1. This is 0. Here we have our relative min. Here we have our relative max. Here we had no information, and it turns out that there's neither a minimum nor a maximum. Okay. Any questions about this? So on Monday, I think I'm going to spend a lot of time doing exercises on concavity, as well as any other homework problems you want to ask me. But it really is quite important. If you are keeping track of what is going on Monday, that's lesson 20. That's limits at infinity. On Wednesday, we do optimization. The following Monday, we review. And the Wednesday after that, which is the 18th, we have the second exam. So the second exam is exactly 2 weeks from today. Worth keeping that in mind. Okay. Are there any questions about anything that we've done? If not, we will quit. I'm surprised actually that so many people are in class today. I thought a lot of people might be up all night watching election returns, but it's, in any case, if you were, take a nap. So that's it for us. See you all next Monday. Right. Bye, all.
Bye, Professor.
Bye.